about SeqGAN, sequence generative adversarial networks with policy gradient. This paper is published in 2017, so it is earlier than the BERT and GPT-2 and GPT-3 models. SeqGAN is a famous concept in NLP, so today we will have a deeper look into how it is working, and we will understand the concepts together. The paper first mentioned the most common approach to training an RNN is to maximize the log predictive likelihood of each true token in the training sequence given the previous observed tokens. What does this mean? I copied an image from here, and from this image, we see what we usually do when we are building the generative models. So what we usually do is, given the input token, which usually is the previously generated token, we send it through the models and we get the output. We want to maximize the log likelihood of this of the true token given this input. So by getting the by maximizing the log likelihood of this, we train the model and get the parameters and update the parameters. Okay. However, this paper mentioned that the maximum likelihood approach suffer from the so-called exposure bias in the inference stage. So meaning the model generates a sequence iteratively and predicts next code token conditioned on its previously predicted ones that may be never observed in the training data. So this means if we generate something here which is run, and this run token will be fed into the model again. So probably this run token have never been seen by the model during the training time. So this will make the next the future generated tokens even have even worse quality. And it mentions the cumulative along with the sequence and may become prominent as the length of the sequence increases. To deal with this paper proposed a scheduled sampling approach, which means they do teacher forcing first by sending the actual or true input at every step when they just started to do the training, and gradually they change to the previously predicted token as the input. However, this paper showed that the schedule sampling is an inconsistent training strategy and fails to address the problem fundamentally. So this means during prediction, we are generating the token one by one. However, when we're evaluating the result, what we actually see is the quality of the whole sequence, not the generated token at every step. So even with schedule sampling, we still haven't dealt with this inconsistency fundamentally. There's another possible solution to the train inference discrepancy problem, which is to build the loss function on the entire generated sequence instead of each transition. This paper, they propose to use the blue score to guide the sequence generation. The blue score is for the whole sequence, so this can tackle the train inference discrepancy problem very well. However, metrics like blue score may not be the perfect matrix for the tasks. For example, for poem generation and chatbot, it is very, very hard to find a matrix that is directly available to score the quality of the generated sequence. So, how to get a kind of score to accurately evaluate the quality of the generated sequence becomes the key problem. To solve this, the author of this paper find the general adversarial net, which is GAN, is a promising framework for alleviating the above problem. As a short description, the paper mentioned in GAN there's a discriminative net D nerves to distinguish whether a given data instance is real or not, and a generative net G which nerves to confuse D by generating high quality data. In poem generation task, for example, D needs to distinguish whether a given poem is generated by machine or it's real, and the generative net G needs to generate high quality poem that can confuse D. To understand deeper about GAN, let's look at the generative adversarial nets paper. In this paper, we can look at the objective function of GAN. Here, the objective function is the log likelihood of making a correct prediction. We want to maximize this log likelihood over the discriminative model D. Also, minimize this objective function over the generative model G. The log likelihood of making a correct prediction can be expressed like this. It comprised of two parts. The first part is when the data is from the real distribution, and here we take the log of the output from the discriminative model. On the other hand, when the data is from a random distribution, we first feed the data into the generative model G, and then feed GZ into the discriminative model D. Here we get the likelihood of GZ being the real data. By calculating 1 minus the GZ, we get the likelihood of D making a correct prediction. Back to our sequence GAN paper. This paper mentioned applying GAN directly to NLP problem. It has two problems. Firstly, GAN is designed for generating real-valued continuous data, but has difficulties in directly generating sequences of discrete tokens such as text. By this, it means if we look at the objective function for fixed D, if we update G a little bit, this output GZ here is not continuous. It cannot change slightly from one output to another output. It can only change from one token to another token, which is discrete. If this is discrete over G, this whole function is discrete over G, meaning it is impossible to get the gradient here. And so it is impossible to do gradient descent like we normally do in GAN. The second problem mentioned by this paper is that GAN can only generate the loss or score for an entire sequence. For partially generated sequence, it is non-trivial to balance how good as it is now and the future score as the entire sequence. As we know for NLP generative task, it is not enough to have only one score for the entire sequence. What we need is to have a score for every step to guide the next token generation. To address the above two issues, this paper proposed to use reinforcement learning. Before we continue, let's look at the key elements for reinforcement learning. This is a really good blog about reinforcement learning. If you have time, I suggest you to have a look at this in detail. Here, we only look at the key elements for reinforcement learning. In reinforcement learning, there's an agent and an environment. Here, we only look at the key elements for reinforcement learning. If we think about the game of Go, the agent is the players who is playing the game, and the environment is the stones and the board. States is the current stone position on the board, and the actions is a position, and the action is a position you want to place the next stone. Given the state and action you take, the new state is prime is all the stones on the board after you take this action. The final element is the reward R, meaning given the current state S, how much your action A contributes to your finally winning the game. As we can imagine, this reward R is not directly available because what we have is who finally wins the game, but not a reward for every step. Therefore, many research deals with how to estimate reward, and many research deals with how to get the next action. Back to our sequence GAN paper. This paper mentioned they are training a theta parameterized generative model G theta to produce a sequence y1 to t. At timestamp t, the state S, which is this element, state S, is the current produced token y1 to yt minus 1, and the action A is the next token yt to select. The probability of an action given the current state is called the policy model. Here, they expressed it by g theta yt given y1 to t minus 1. The state transition is deterministic after an action, meaning that if we know the current state is y1 to yt minus 1, and we already take the next action being yt, then the new sequence is y1 to yt, and it is fixed if the state and action are fixed. They also train a phi parameterized discriminative model d phi, where d phi y1 to t is a probability indicating how likely a sequence y1 to t is from the real sequence data or not. To train the model d phi, it has positive examples from the real sequence data and negative samples from the synthetic sequences. So this is a normal classification problem. The only special thing is that the negative examples is from the synthetic sequences. So now we already have the state, action, and new state. Next, let's look at how we define reward R in sequence GAN. The paper mentioned that there's no intermediate reward. The objective of the generative model, g theta yt given y1 to t minus 1, is to generate a sequence from the start state S0 to maximize its expected end reward. If we use RT to denote the reward for a complete sequence, the expected end reward is the expectation over RT given the start state is 0 and the theta, which is the parameter for the generative model. If we define this as the end reward given the current state S and the action we take, we can, we can express the expected end reward as the weighted sum of this action value. The weightage here is the probability of transit to y1 given the current state is 0, and we sum over all the token space. Okay, this looks like a nice expression of the expected end reward. But now the question comes, how to define this action value? If we use the discriminator d phi as the reward, it is quite clear that if the current state is y1 to t minus 1, and after taking yt, we get the whole sequence y1 to t. And the action value for the whole sequence is equals d phi y1 to t. Okay, this looks fine for the last timestamp, but what should we do for the intermediate timestamp? The discriminator only provides a reward value for a finished sequence. However, what we actually care about is a reward at every timestamp. So how to do that? The author mentioned that we should not only consider the fitness of previous tokens, but also the resulted future outcome. Therefore, to evaluate the action value for an intermediate state, they applied Monte Carlo search with the rollout policy G beta to sample the unknown last t minus t tokens. They represent an anti-Monte Carlo search as this. So basically, they are doing sampling for big T minus small t steps and for n times. And they get n samples of y1 to t. And after doing this, use dphi to get a score for every generated sample and taking an average of them. However, when t equals the last timestamp, they just use dphi to calculate the score directly. This paper mentioned that in their experiment, d beta is set the same as the generator, but yes, you can also choose other rollout policies as well. So now for sequence GAN, we have already defined state, action, new state, and reward. The state is the generated token so far, y1 to y1. The state is the generated token so far, y1 to t minus 1. Action is the next token to generate, yt. New state is y1 to yt, and reward is defined by this action value q here. So we can see in this paper, in sequence GAN, the g theta here is nothing special from our normal generative NLP model. It's also generating one token after another. This d phi here is also nothing special. It's just a normal classification model with the positive samples being the real data and negative samples being the synthetic generated data. What is special in this paper? The special thing about sequence GAN is the loss function. The loss here is different from the normal generative NLP model, which is defined by MLE. It is defined by this weighted sum of the action value. And the action value here is calculated by taking some samples. The loss function is well defined. However, when we are trying to do gradient descent with this loss function, we face some problem because here we do some sampling here with g theta. If we want to take derivative against theta, how are we going to calculate that? The next part of this paper here is about how to get the gradient of this expected end reward with respect to the generator parameter theta. The final target is to take gradient over j theta. However, we can see j theta, inside j theta, there's a multiplication of these two terms, and one of the terms here includes some sampling, so it is not easy to take gradient directly of them. And this paper proves that the gradient of j theta equals some expression which only includes the gradient of this g theta. So this looks really nice. So the detailed derivation is provided in the appendix, but the basic idea is if we take gradient of j theta, it equals the gradient of the first term multiplied by the second term plus the gradient of the second term multiplied by the first term. And the gradient of j theta equals the sum over every timestamp, the expected value of the weighted sum. of the gradient of the gy given y1 to t minus 1. Okay, this looks really nice compared to this one because the gradient is only over this g theta. However, there's another difficulty in this because we have to take expectation over all the y to t minus 1. And this is impossible because it's a huge space. The author, they approximate the expectation E by sampling method. So instead of calculating this expectation term, they just sample y1 to t minus 1 to get an unbiased estimation. So this equation 6 becomes 7 where we don't have this expectation term. Instead, we have a sample here, y1 to t minus 1, and everything else are the same. And after we come to this, another difficulty comes because we have to sum over all the yt in the token space, and this is huge also. What they do is that they change this term, the gradient of g theta, into g theta multiplied by the gradient of log g theta. And if we do simple calculation, it can be easily shown that this gradient over g theta equals these two terms together. And after we have this, if we treat this part, this g theta, as a probability, we can change this into the expectation over the last two terms. And again, this expectation can be approximated by sampling method. And we can see, given d phi and g theta, this term is fixed. And for this term, it is just the same as the normal. It is just the same as the normal generative NLP model. So this one can also be easily calculated. Therefore, we get this gradient. However, note that here we are not doing gradient descent, we are doing gradient ascent because the objective function here is the expected end reward and we want to maximize it. In summary, the algorithm is shown as here. First of all, we initialize g theta and d phi with random weights theta and phi. We pre-train g theta using MLE, which is the same as what we normally do, and we generate negative samples using g theta for training d phi, and we pre-train d phi via minimizing the cross entropy. So this is also what we normally do for a classification issue. And then for g steps, we generate a sequence y1 to t, which satisfies the current g theta. And for t in 1 to t, we calculate this action value with equation 4. Equation 4 here. So this is known, and the rollout policy is also known. And finally, we can update the generator parameters with policy gradient using equation 8. Here is equation 8, where this gradient is calculated by this. This is the action values, and this can be calculated as we normally do. And we approximate this expectation using sampling method. Therefore, we can get this gradient. Now we have already updated g theta. And for these steps, we use the current g theta to generate negative examples and combine with the positive examples and train the discriminator. And we do this we do this repetitively until the sequence GAN converges. This paper mentions that they use LSTM for the generative part, and they use CN as the discriminator. Yes, as we mentioned, there's nothing special for the generator and the discriminator. The only special thing is about the loss function. For experiments, this paper used a randomly initialized LSTM as the true model. They call it the oracle. So they use this to generate the real data distribution, PT, given the previous timestamp sequence. How they evaluate this is that they first train the sequence GAN, and then they generate sequences with the generator. They calculate the negative log likelihood of the next token given the previous tokens. So this one is the lower the better, meaning the oracle thinks the sequences generated by the generator is real. And they compared with first of all randomly token generation, and second is MLE, and third is scheduled sampling, and fourth is policy gradient with blue. The fourth one is they use blue score to guide the generation, and they show the results here, meaning the oracle thinks the sequence generated by the sequence GAN is most real. Okay, so this is pretty much about this paper. A final thing I want to mention is that in a lot of recent works, we seldom see sequence GAN. It is because some papers, like this one, mentioned that the GAN models, although it guarantees quality, but it ignores the sample diversity. They mentioned that exposure bias appears to be less of an issue than the complication arising from non-differentiable sequential GAN training. And also, MLE trained model provide a better quality diversity trade-off compared to their GAN counterparts. Its MLE model being much easier to train, easier to cross-validate, and less computational expensive. Okay, so that's all for this paper. Hope you have a deeper understanding of sequence GAN. Don't forget to like this video if you enjoyed it. Thanks. See you next time.